Hey Sky, are you playing with that fidget spinner again? I hear that all the cool kids have them.
Yeah, actually.
What is it? Is it something about their well-oiled bearings that makes their rotation hypnotic?
I think it's actually supposed to be like a fidget toy.
I see. What does that mean?
I don't know.
Have you ever thought that if you spun those fast enough that you could actually cause them to fly apart?
Now that you mentioned it, yeah.
Yeah, because you know what, I thought it'd be cool to actually do the math for that, because I like doing the math of spinning up asteroids and stuff. Yeah, so there it goes. How fast would we have to spin it? Well, we can use the power of math to find out. I'm going to use math. I'm going to use measurements. So what I'm going to do, right, first of all, we need to know how heavy this is, right? Because if we spin this fast enough, these things will overcome the strength of the plastic and the thing will fly apart. So this is like 3 weights that are roughly the same, and in the middle there's a bearing, which I think is probably about the same weight. So if I take the weight of this and divide it by the 4, that'll give us roughly the weight of all these lobes.
So it gives us about 52.
So 52 grams, okay? So that's 0.052 kilograms, right? And divide that by 4 is, of course, 13 grams, right? 0.013. Now, the next thing is, we're going to figure out how it will fly apart. Now, it will fly apart because the plastic will break. Now, you might look at this and say, well, this is the narrowest part here, right? This is the part that's going to break. But I look at this a little harder, and what you see in here is this is the bearing. So the plastic is actually just these little lobes here. These are much narrower. And so each lobe is held up by 2 of these. Turns out that all we need to do is measure one of these, and that will be the braking force that we get from this, right? So it's kind of obvious. It's kind of not obvious, but it is obvious to me. So this is about half a centimeter, right? 5 millimeters, and it's about 7 millimeters thick. I wish I had calipers. So the cross section of that is roughly, and I mean very roughly, it's about 0.005 times 0.007.
35.
It's 3.5 times 10 to the minus 5, right? That's what it is. 3.5 times 10 to the minus 5. Now, the strength of material is measured in megapascals, right? Pascals are force by area. So that's the point at which the force over that area exceeds the capacity of the plastic to hold on. Now, things like polycarbonate and acrylic, when they're perfect, they can get something like 70 megapascals. I'm going to say this probably isn't as good, but we'll still say it's pretty good. So let's say 50 megapascals strength, right? 50 MPa, and actually that might be an uppercase P. So multiply 50 megapascals by that, right? So 1750 newtons, which would imply, right, that if you took something and used this to hang somebody from it, that the breaking point would be roughly 175 kilograms, which I think that's being very generous. We could test this, but I would break it, right?
Could we test that with Orion?
Yeah, he'd probably be able to hang from this just fine. But yeah, that's 2 large individuals, so maybe I'm overestimating this here. Now, the next question is, how much force does one of these things exert when it's spinning, right? So we need to know the distance from the middle to the very edge here, or to the middle. What we really need to do is we're going to take roughly an average. We're going to take the center of this. And using my terribly inaccurate ruler, I'm going to say that's 2.7 centimeters, right? So R is equal to 0.027. And what we really want to know is the velocity of the rotation, or the speed of rotation where that happens. So we know from physics that the force is equal to mass times the velocity squared divided by the radius of rotation for centripetal force. And flipping that around, that implies that the velocity is equal to, or the maximum velocity is equal to the square root of the force divided by the mass times the radius. So we have all those numbers. So the force is 1750, multiply that by the radius, which is 0.027, and then divide that by 0.013, and that gives me 3,634, and if I take the square root of that, I get 60 meters per second to the minus 1. How many RPM is that? Well, 60 meters per second, we're going all the way around, right? So we divide the speed, 60, by the circumference. So we divide it by 0.027, and divide by 2, divide by pi, and we get 353 rotations per second times 60.
354.
Okay, no, but it's 21,220 RPM equals boom, or RUD. RUD, which means rapid unplanned disassembly. And yeah, those things would fly out at a couple hundred miles an hour, so probably wouldn't kill you. What? I don't think so. Not unless it not unless it really hit him in the wrong place.
Have to find another plan.
Yeah, we'll have to find another plan. But yeah, look, the math shows it, right? You can spin it that fast and it'll probably break apart, right? Using the magic of full-on physics and math. Did you know that? Could you appreciate that, Sky?
Wow, really interesting.
So yes, if you like your fidget spinners, try not to spin them at the speed of a high-speed racing car, because otherwise they will fall apart.
Yeah, I really believe you can do that.
Someone's going to try it. It's the internet. I'm Scott Manley.
Fly safe.